All right, welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is Wednesday, our second, actually this is our saddest day of the week. Because tomorrow's a test day. We love test days. So you're right, today is a very sad day. There are a couple things I wanted to clean up for topics in thermo. There's a request that we also go over a couple of the worksheet questions, so I'm gonna try and be as streamlined as I can. So stop me if I go off on tangents. All right. So if you've been watching the other videos, or if you were here, I guess last week, we talked about the Carnot cycle, right? And what cool thing can we say about the Carnot cycle?
Most efficient possible cycle.
It is the most efficient cycle heat engine between any two temperatures. I feel like not all the lights are on. I feel like I'm being this is insane. Okay, leave walnut alone is the moral of the story. Okay.
Can we say that temperature falls and rises with entropy? In the Carnot cycle.
So over one full cycle, as I hope to get to, the change in entropy is 0. And we'll see that that's because at one point the entropy is increased and another point it's decreased. So the Carnot cycle is somewhat straightforward, examined on a PV diagram. Yesterday's problem session video, we looked at the Carnot cycle on temperature against entropy plot instead, which again I find interesting. So on a PV diagram for the Carnot cycle, it's made up of a pair of isotherms connected by a pair of adiabats, and so I will try my level best to sketch this in a way that so this might be TH. Well, this is not turning out the way I wanted it to, but this might be TC. So T high, T low, T hot, T cold, whatever your preference is in that naming convention. So we have a pair of states connected by an isotherm. Then we have an adiabat, that is a horrible adiabat, getting us to point C. And then we have another rather poor attempt at an isotherm, and finally another adiabat. So A to B to C to D back to A is our Carnot cycle, and you'll recall that the efficiency of a heat engine goes as the work done, the work of the engine, divided by the energy and as heat on the high temperature side. So in general, we can write this as QH minus QC over QH. That's kind of tried and true from last week. For our Carnot cycle, we can even further simplify this as 1 minus QC over QH. And this comes about because QC over QH is the same as TC over TH for our so I guess the Carnot piece comes here, right? This is still true here, QH over QH, right? Is that all right? So, I'm, in the interest of saving a couple minutes so that we have a chance of getting to some of the worksheet questions, I was going to detail how to get to this, and it's not a very long derivation, but I think that I will turn you to your textbook for that, as opposed to doing it now.
I agree.
Okay. It's pretty straightforward, taking advantage of these two known temperatures, and that A and B have the same temperature, and that C and D have the same temperature, and that B is connected to C by an adiabat, and A is connected to D by an adiabat, and that there is, just as PV to the gamma is constant for an adiabat, we can also go to TV to the gamma minus 1 is constant, right? So, and so with that you can demonstrate that this is true. You also know that for the adiabat, no energy enters as heat. But it's a pretty standard derivation, so you can find it in your textbook, you can find it on Google. Okay, so with that in mind then, I want to turn us towards entropy. So, done a few entropy problems on the problem session recordings. Additionally, you guys did some lab stuff on this. I posted the worksheet solution from the lab manual to your Canvas site, and you can see an entropy problem there also. So you've seen a few entropy problems already. I'll give you kind of this Clausius statement. I think this is from the 1860s, roundabouts. good statement of what entropy is provided by Clausius, but there's a few ways of calling entropy. Arose by any other name, right? But this definition, I think, encapsulates a lot of it. So, we talked about microstates and macrostates in lab last week. So, just as kind of a quick reminder, microstate is a particular configuration of the individual constituents of the system. And then there's also macrostates. So macrostate is a description of the conditions of our system from a macroscopic viewpoint. That sounds a little circular. So a particular microstate might be something like half the molecules are moving to the left with V naught and half the molecules in this room, air molecules in this room, are moving to the right with some speed V naught. That would be a very, very ordered way of arranging the air molecules in this room, right? Another might be that the air molecules in this room are moving in random directions. That's definitely a less ordered descriptor of a much less ordered microstate, right? And so notice that there aren't a whole heck of a lot of ways of getting half the air molecules in this room to move to the left and half to move to the right with speed V naught, right? That's it's very, very ordered. It's a very, very specific. There's not a lot of ways of getting to that. So it's not very likely that that's going to be manifested. That's kind of this Clausius description of entropy. Is that all right? Okay, so macrostates typically have many, many, many different microstates that will get you there. And we talked about that with coin flips. We talked about that with dice. So the process that we're going to use is we're going to assume that any particular microstate is just as likely as any particular other microstate. It's just that if there are more microstates that lead to the same macrostate, that macrostate is going to be preferred. Does that logically stand? Okay. So, I guess really, really going all in on this. There are just more disordered states than there are ordered states, right? And so if each individual state is as likely as every other state, since there are more disordered states than ordered states, it's likely to go from a more ordered state to a less ordered state. Yeah?
So there's always a larger probability of disorder?
There's just more ways of manifesting that than there are of ordered states, right? And so if every time you shuffle the deck, right?
They're never going to be back in order.
It's more likely that you're going to get to a disordered state than you'd start with
Numerical order.
In suit and in rank order, and then shuffle the deck. Well, that state is just as likely as every other state out there, right? It's just that there's a lot of other possible ways that the cards could be arranged.
Right.
And so, getting back to that one specific state again is not very likely. Does that make sense? That works?
Yeah. It works.
All right, so I'll tell you also that in any real physical process, entropy increases. The best you can hope for is it stays. Best is a normative statement, but the best you can hope for is that it stays the same. But in any process, it stays the same or increases. Realistically, in any process, it's going to increase. So will you make sure to stop me with at least, 15, 20 minutes so that we can get through stuff? So, as you've seen over the last week or so, ds can be written as dq over t. And so, entropy is a state variable. And so, typically, regardless of the path you actually took to get there, we pretend it took a fully reversible path, because that makes it easier to calculate. And since it's a state variable, as long as what you care about is the starting and ending values, or the difference between them, then the path you took to get there we're less worried about. So pick an easy path is kind of the way we play this game. So typically we'll do this for energy transferred as heat along a reversible path. That's what I mean by QR. And so we'll say that dQr is less than 0 if energy is expelled by the system. As heat. And dQr is greater than 0 if energy enters the system. So again, if you watched the problem session video, said this kind of enough to probably drive you batty, but when I see something of this form, I feel compelled to integrate. And so if I integrated both sides, oops, it's not me. What I get on this side is delta S, and on this side, well, I have dq over t from the initial state to the final state, earlier state to later state. Is that all right? So, coming back just quickly, I'll move this away in a second. To our Carnot cycle, remember this path and this A to B and C to D are what kinds of processes? Isotherms. B to C and D to A are what kind of processes? Adiabats, right? And so what's true about B to C or D to A?
Q equals 0.
Q is 0, right? And so for that, if, and so that this comes in on camera, heat is entering the system in which of these?
AB to
AB, and where is it expelled from the system?
DC.
So C to D, yeah? And so in my, again, this is a bad cartoonish description of what's happening, right? But I'm going to call this QH, and I'm going to call this QC. Yay?
If it's an isotherm, delta T be 0.
Yes, right? So I tried to draw this, and I recognize it's not a good drawing. But this dashed line represents the high temperature. And so everywhere on this path A to B is at 1 temperature. And everywhere on this, so this is a different isotherm of T low.
So how does
and
heat
from
enter and leave if delta T is 0?
It's coming through work done, right? So either work done on the working medium or work done by the working medium.
So you see that like an internal energy.
Yeah, so the internal energy isn't changing, right? Because that's tethered to temperature. But in order for work to be done or for it to do work, right? But not change the temperature, that means that there also has to be heat in or heat out. Yay? So as this gas is expanding, right, it's going to a greater volume from A to B. Is the gas doing work on the environment, or is the environment doing work on the gas? It's open to all.
Gas in the environment.
So as the gas expands, it's doing work on the environment, right? Which means it's giving energy away. In order for it to give energy away but not lower its temperature, what has to happen?
Energy has to come in.
Energy has to come in as heat. Yay? What's happening from C to D? Is the gas doing work on the environment, or is the environment doing work on the gas? The environment is doing work on the gas from C to D, right? So in that compression, right? So for that to happen, work done on the gas, but the gas isn't changing its temperature, what has to happen there? Well, it has to expel energy as heat. Otherwise, the temperature would change, yeah? So if we looked at those 4 stages, note that there's something cool going on here, specifically for our Carnot. Where does the entropy not change?
What is it?
Wouldn't B to C?
It's not going to change on the adiabats, right? Why?
Because heat doesn't.
Because there's no exchange of heat, right? So where does entropy change? A to B or C to D, yeah? So, but what's nice about, say, A to B, what's true of the temperature?
Constant.
Constant, so what am I allowed to do in the integral?
We'll see out.
It can come out of the integral. And so we can say for the high temperature isotherm,
Delta S equals Q divided by T.
delta S is equal to QH over TH. Yeah? What about from C to D?
Q0. Or, no.
C to D. I already conceded that B to C and D to A are 0.
TC over TC.
Plus or minus, looking at our definitions. So, did I go with QC and TC?
Yeah.
So, in that case, what's the total change in entropy for one cycle?
0.
I'm going to call this A to B, and I'm going to call this C to D. Are you using the fact that it's a state function to say that it's 0? Which is totally fair, but let's try another route. So delta S total, right, is going to be delta S A to B plus delta S C to D. And I can also say that B to C and D to A, the delta S's there are 0, and so they're not really, I could add those in, but it's like adding 0 twice, yeah? And so this is QH over TH minus QC over TC. Yay? But recall right here, that we said that for the Carnot cycle, QC over QH is TC over TH. And so QH over TH is equal to QC over TC. Yeah? And so as you guys rightfully stated, for the Carnot cycle, this is 0. What I would tell you is that it's actually true for any reversible path. Reversible cycle, sorry. That's not how you spell cycle. Cycle. But it's easier to show for the Carnot cycle, so I'm going to be lazy. Is that kind of all right? Let me do a couple of, and this ends at what? 55?
55.
I had more time than I thought. Okay, so I'm going to do a couple examples here. I may actually go back and derive this for you, but I do want to carve out a little bit of time at the end so that we can look at some of the worksheet stuff.
I have a question.
Yeah.
If the temperature changes, do we still use the same formula?
So I'm going to give you a shot where, right now, where the temperature is going to change.
Okay.
So 12. I'm going to do 3 examples in rapid succession. The third one is the one where the temperature is going to change. So solid with latent heat of fusion, LF, melts at a melting temperature, Tm. And I wanted to look at the entropy here. The change in entropy, at least. So note that we still have that delta S goes as dq over T integrated. But do you remember, how does Q relate to the latent heat? Yeah, it's just M times L, right? And so note the other thing is that unlike the goofy example I gave you in our worksheet, the way solids normally melt is they melt at one temperature, right? It's the issue with butter is that it doesn't melt at one temperature. That's why I gave you the simplification in the worksheet that you could just pretend it does. That was the blurb at the end, is acknowledging it really. It's much more complicated than this. So T can come out, right? And so that's just going to look like MLF over T. We could do the same thing if instead it was a liquid that was vaporizing, right? We'd also do it as a liquid that's solidifying. Just in that case, the entropy, rather than being positive, would be negative. Yeah. Sorry. So, if we did this for an ice cube, latent heat of fusion somewhere around 3.33 times 10 to the 5 joules per kilogram. And so we did this for, say, 1 kilogram. What would we expect? So delta S melting 1 kilogram of ice at 0 degrees Celsius. I'm picking this specifically to illustrate a point.
Can we just plug it in?
Sure. Help me.
1 kilogram times LF.
273.
Why 273?
That's the absolute temperature.
Because I don't want to divide by 0, right? Mr. Hilton told me when I was in 8th grade, divide by 0, go straight to hell.
12.20.
I went to a parochial school, so they meant it.
12.20.
He told me that on other occasions too, but that time he really
1,220.
what was it?
1,220.
1,220. What are the units?
Joules per Kelvin. Kilogram Celsius.
As it must needs be. Yay? If you're multiplying two temperatures together or you're dividing temperature, you need to make sure you're using Kelvin. Don't use Celsius. Hooray?
Yeah.
Okay. So let's look at the so-called free expansion. So I don't know, call it V earlier and delta V. So let's imagine that you have a gas that is trapped in the left side of this container. And maybe there's a thin membrane here, maybe there's a card. Whatever we're going to do, we're going to remove this as a barrier, whether we break the membrane, whether we just remove it. The gas in here is going to expand to fill the whole available volume. Yay? But we call this a free expansion because is there anything the gas has to push against in order to access this new volume area? Not once I remove the membrane, right? And so in that case, if there's no pushing, right, is there work done? And so that's why we call this a free expansion. It's also fast enough that it's going to be hard to add or remove energy as heat, right? And so we could say then that our delta S, well, it's hard to follow this in this free expansion sort of way. And so instead what we do is we choose to look at this in a reversible fashion. We pretend that was done reversibly instead. Since entropy is a state variable, it only cares about the final state, right? And so we can say that the change in entropy, once we break this, looks like we had followed a reversible path instead. The temperature won't change though, right? Because we just said
There's no work done, so the temperature doesn't change.
no work, and we're not letting heat in or out, right? So the internal energy can't change.
Right, it's not going anywhere.
And so we can do something like that. And And so now we can follow kind of the more traditional fashion of NR times ln. I guess that's V earlier plus delta V over V earlier.
Are you derive that?
So where have we seen something like NR times?
Is that ln?
Yeah, as well.
This is our natural log, yeah.
Okay.
Yeah.
Oh, got you. Okay.
Forgive me, but for the whole semester, I'm just gonna.
Okay, I got confused because I think that was ln for the like vaporization or something.
I apologize. I don't know how to write cursive, and I don't really write lowercase very well. So, yay. So let's try the calorimeter one, which allows for the temperature to change. And then I think that we should still have time to do some of the worksheet stuff for you. Chris.
That doesn't make any sense. The
Uh-oh.
DQ is, you said there's no change in heat energy, so I don't
Well,
understand.
we can take this through another path that that is done reversibly. So it may not really have been done slowly in a way that we move so gradually that we can always step back from where we were. So let's imagine that we just did this in a completely isothermal fashion, for example.
What is isothermal?
That's a good point.
Oh, yeah.
But let's imagine that we did it isothermally but slowly. So in that case, for an isotherm, how does work relate to Q? How does W relate to Q?
Very cool.
Is that fair? Magnitude wise? So let's say
Oh, so there was heat added, there's just work, there's no work done. The work is zero.
when we actually did this, we free expanded this, but we can pretend that we did this in a very, very slow isothermal expansion. It's a state variable. The entropy doesn't care how it got there, right? The entropy is what it is.
Yeah, it's zero.
Well, it wasn't even zero when it was all trapped here, right? The change in entropy is also not zero, though, right?
Entropy is zero when it's a cycle, right?
The change in entropy
Yeah, the change in entropy.
for a cycle done reversibly, yeah.
Yeah.
So
And this is not reversible, right?
this is, you cannot undo this.
So that's why it's not zero.
So, right? Well, we also didn't even bother bringing it back to its prior state. So this wasn't a full cycle.
I don't think I understand the difference between DQ and DQR.
DQ, I want you to think of what really happened. DQR is heat that entered or left, energy that entered or left as heat reversibly.
What does that mean? What do you mean reversibly?
I mean that we have done this so gradually that we have never gone so far from the last equilibrium spot that I can nudge it back to equilibrium, no harm, no foul. And so if we do this in a bunch of tiny little steps like that, we can go from here to there in a way that is quasi-static or quasi-reversible, right? And so what I'm saying is, it's definitely true that it didn't take a reversible path to get from here, from this volume to this volume. But it also doesn't matter, because the thing that we're looking at is just state dependent.